Right, sorry about the hold up. All right, so first things first. So remember, there's not going to be thank you, so-and-so assessment this week because we've got the test on Saturday, right? So the next so-and-so one won't be due till next week, right? So we do have your next test coming up. Now, obviously, we had a problem with the room booking for test one. You might recall the room was a bit too full because let's not get into that, that annoyed the hell out of me. So this time I've booked a third venue, right? So if you're, let me read it. So it's this Saturday, 9:30 till 10:30, basically the same deal as test one. The only difference will be if your surname starts with A or B, go to Math Lecture Room 1, right? Or it's also called the Cheryl Prager Lecture Theatre, but on the timetable, not timetable, on the campus map it's still called Math Lecture Room 1, right? So it's in the math, it's a big lecture room in the math building. So if your surname starts with A to B, so that's about 50 people from my class list, go there, right? And everyone else go to Tattersalls and Willsmore, which is where we held the first test, okay? That way we won't have this problem I had last time. Same deal as the first one, though. It's an hour long, start at 9:30 on the dot, and the formula sheet will be provided attached to the end of the test paper. All right, I've also told that the Math Union is going to organise another study night. Right, so that's this Wednesday. Yes? What's the date today? Yes, the Wednesday the 8th. We want to be this week because then it'll be useless. Right, from 4 till 6 in the Hemsley Learning Suite. I have no idea where that is. Right, but obviously it's in the Reed Library somewhere. I assume it's where the first one was?
It's in the purple room. There's a purple room in the library, so it's a bigger room, I think.
Oh, okay. It's in there somewhere. You'll find it, right? Now, there'll be experienced tutors and free pizza, and then to top it off, right, there'll be an integration competition. How exciting, all right? All right, I'm going to go. I want to win, all right? There'll be an integration competition from 6 till 7. It will feature, what's it say, all the integration techniques up to triple integrals, though triple integrals aren't in the test, so, right, the triple integrals are only up to double, the test only covers up to double integrals, right, but it's perfect, obviously, for Math 1011 revision. Who's doing Math 1012? Have you done improper integrals yet? Is that in the test this week for 1012? Well, good practice for you too. Then first prize will be a Math Union t-shirt and some chocolate. All right, awesome. All right, so make sure you go there. Now there is a practical class on it's about that time, right? That if you want to just explain I think there's a practical class on from, I think it's 3 till 5, is it, that day, on Wednesday? Now, you can, if you want to go to this, you can leave at 4, right? Just I'll explain this to the person running it. If you want to go to this instead, and your attendance will be recorded, okay? Right, I've also uploaded a sample test, basically the same deal as the first one. Again, I think you'd agree that the first test for the first test, the sample test was a good indication of the type of questions and the level of, except for the last question, of course. Right, so, but keep in mind this will only cover what we covered up to lectures in week 8. So what you covered in the practical classes last week. So what we covered in the lectures last week and what you're covering in the practical classes this week will not be in it, including the last question. Right, because if you've got your practical class on Friday or something, it's not fair. Right, and I'm not uploading solutions till Friday. So this stuff that you're covering in the practical class this week will not be in it. So it will cover up to standard double integrals, right? So no change of coordinates and no triple integrals, okay? Right, so I've uploaded a sample. So the first question is going to be something about locating and classifying critical points, Taylor polynomials. Then obviously we cover the big thing we covered is integration and integration strategies, right? So there's going to be one on a couple of things, and it'll cover all. I could ask any integration any integration technique except the half angle substitution, the T substitution, that really weird one. I ain't going to ask that one, right? But all of the rest, so basic substitution, trig substitution, inverse substitution, partial fractions and parts, what's covered. Everything but the half angle one, all right? So this one's an inverse trig. This one's a partial fractions, this one's a integration by parts, right? And then a standard double integral, right? And then as always, as with the first test, right, the last question will be something to test your understanding of what we've been doing. It won't be heavy algebra, it will be more testing your understanding of what we're doing. But keep in mind, it's only worth 5 marks out of 30, so if you're stressed about it, don't. Right? It's better you answer 6 questions well than 7 questions terribly. Right? I've uploaded work solutions for the first 6 questions as well. You're welcome to ask in your practical classes this week if you want some help with the sample test or anything about the test this week. All right? Remember also I have consultation on Wednesday from 9 till 12 if you want some one-on-one help with me. All right? Are there any questions about the test this week? Anything at all? No? All good? Excellent. Okay. All right, but don't forget about the study night and things like that, so get some extra help. All right. Right. Now, what we did last week is we started to look at basically doing a change of variable in double integrals. And as I explained, unlike integration of function of a single variable, where essentially we use a change of variable, or if it's a definite integral, you could call that a change of coordinates as well. And it's always, for a function of a single variable, it's always motivated by we can't integrate the function, right? We need to do something with it. With double integrals, and we'll see soon triple integrals, we often do a change of coordinates not because we've got something that we can't integrate, although that can happen, but that's not what we're going to do. I went through one example last week where that's what it was. The change of coordinates was motivated because we couldn't integrate the damn thing. But in tests in the final exam, although this isn't going to be in your test, so in the final exam that's not going to be the case. It will be motivated by the region you're integrating over. There's something wrong with it. Right? Either we've got to split it up into too many pieces, or it has some sort of circular symmetry so that polar coordinates helps greatly in solving the thing. Right? So one of the things we did last week is, so for a double integral, you remember you're integrating a function of 2 variables, so that sits in 3-dimensional space, and you're integrating that over a region, a 2D region in the xy plane. And if that region has a circle in it, basically, polar coordinates will make life easy. We went through the change of coordinates for polar coordinates. Just replace x and y with r cos theta, r sin theta. The Jacobian is just r. You'll never have to recalculate it. I give this to you on the formula sheet. Right? Now, we can extend this idea to triple integrals. The problem here is that coming up with a suitable coordinate system is a skill that comes with lots and lots of practice. That is not something I expect you to be able to do. Unlike double integrals, where I may give you one where you have to come up with the change of coordinates yourself, in triple integrals, I will never ask you to do that. I will tell you what to do. Right? And we are only going to do two specific types of coordinate systems in 3D. But essentially, all the ideas we went through are the same with double integrals. Right? So you can basically set it up there. Again, this is proved in the unit reader. This is quite complicated to prove, but basically you get this formula. Right? So what you need is a change of coordinates that takes your x, y, z coordinates into three new coordinates, which here I've just called u, v, w. Call them whatever the hell you want, of course. And then your change of variables is x and y and z replaced with these functions of u, v and w. The absolute value of the determinant of the Jacobian matrix, or just the Jacobian in this case, because it's three old variables to three new variables. And again, we have this absolute value, which makes sure that, because what we're technically calculating here is volumes, so we need everything to be positive. Right? Now, what we could do is we could start going through examples where we map some 3D region into a nicer. That's very complicated because you have to be able to visualise very accurately what's going on, not something I'm going to get you to do. So what we're going to do in this case is look at two special types of 3D coordinate systems. The first one is just a logical extension of this to 3D. Right? So remember, these are called polar coordinates. In some textbooks, these are called circular coordinates for obvious reasons, because they're circle. You use them to describe circles nicely. The first one we're going to do is called cylindrical coordinates. Now, before we get to that, I want to show you some pictures. Right, so the standard Cartesian coordinate system we use, the x, y, z, that's often called a Cartesian coordinate system, but it's also sometimes called the rectangular coordinate system. And the reason is because planes of constant x, constant y, constant z form rectangles. Right? It kind of looks like this. Right, so in the standard x, y, z coordinate system, now in this book for some reason z's coming out of the page, usually we put z up, but basically you can imagine in the 3D coordinate system we've been working with, lines of constant x are just planes, constant y are planes, constant z are planes, right? So they all basically form rectangles. So often this coordinate system is called a rectangular coordinate system as opposed to a Cartesian coordinate system. Right? And that's what the coordinate planes look like, right? Constant x, constant y, constant z. However, just like with polar coordinates, if you have some sort of circular or spherical deal going on, this coordinate system is not going to help, right? So for example, if you want to find a triple integral over a sphere, using this coordinate system will be hell, right? Because you have you're going to have to bring in lots and lots of square roots to get the limits out, right? Just like with double integral circles, you get plus or minus the square root of r squared minus x squared, or however you want to do it. Spheres makes it even 3D makes it even worse because we've got to do 3 integrals instead of 2. So there are lots of different coordinate systems we can use to match the boundaries of things we're trying to work with, right? And this is a classic old book that lists them all, right? So this is called this is a pretty old book. Please do not take note that I illegally photocopied a copy. All right? I was a poor student and I couldn't afford it. So, all right? And I've had it ever since. I'll buy it one day. It's actually, I think it's out of print now, but anyway. It's a very handy book, and there's different coordinate systems. The first one we're going to do is a logical extension of polar coordinates to 3-dimension, which are called the cylindrical coordinates. Now this diagram's a bit not correct, because you've got x and y in the page and z coming out of the page. Normally I would draw it so z's going up and x is coming out of the page. Right, but basically this is polar coordinates for x and y, and z were acting as normal. Right? So you can imagine planes of constant r here are cylinders, as opposed to circle just extended in both directions. Then planes of constant theta, right? So in polar coordinates, constant r is a circle, in cylindrical it's a cylinder. Right? So planes of constant theta in polar coordinates are just straight lines, these are straight planes. right? Planes of certain angle, oh, what am I doing? Theta, and then planes of constant z are just the standard Cartesian coordinate system. So you would use this one if the 3D region you're trying to find a triple integral over has cylinders in it, or something like that, all right? And it'll make life easier, right? And essentially it's just a logical extension of polar coordinates to 3 dimensions, right? So this is how we define it. Right, so the cylindrical coordinates is basically just a 3D version of polar coordinates. Your x and y variables are the same, right? And we denote this as in polar coordinates xy becomes r theta, and in cylindrical the standard notation we use is r theta xi. So xi is this little Greek wacky looking letter, but it's basically the same as the standard z one. And because I hate writing xi, I usually just write it as z. Because that's basically what it is. Right? So x and y act like your standard polar coordinates. Theta, as always, goes from 0 to 2 pi, and r is linked as the radius of the circle, basically. So now they're cylinders. For a constant z, it's just a circle to a certain height. You extend the circle up and down, you basically get cylinders, hence cylindrical coordinates. Right, so this is what a point in 3-dimensional space looks like in cylindrical coordinates, and you should be able to convince yourself that every single point in a 3-dimensional space can be represented uniquely by some r, some theta, and some xi, which is basically just z. Right, so the coordinate surfaces are basically cylinders. So for r as a constant, they're just cylinders. Right, for they're half planes, the theta is constant is half planes intersecting the z-axis. So remember, theta goes from the positive x-axis going anti-clockwise, just the same as polar coordinates. And then xi or z is just basically the height, right? So if you imagine this table is the xy plane, right? So, and that z's up here. Planes of constant r is just cylinders. Right, like this. Constant theta are just planes that go around like this, and constant z's are just cuts, just like the standard Cartesian coordinate system. Right, that one's not too bad to deal with. The next one, however, is spherical coordinates. Right, this one's a little bit more difficult to deal with. Right, let's have a look at what this one looks like. Come on. Right, so this is what spherical coordinates look like. As the name implies, this is what you would use this one when you are doing something over spheres. Right, so this one is drawn the normal way. So we've got, imagine x is coming out of the page, y is left to right, z's up to down. Right, and everybody does this differently. In this book, it's r theta phi. Because everyone does this differently. How do we do it? We do it rho theta. No, that's r theta psi. We do it rho theta phi. It depends on the textbook and things like that. All right? But basically, we take our x, y, z coordinates and we introduce a new coordinate system, where the first one is the radius of the sphere, and the second one, theta, is the same as the polar angle, so measured from the positive x-axis going anti-clockwise. And then the third angle is measured from the positive z-axis going down, right? So you have rho is the radius, so that's 0 to infinity, basically. No such thing as a sphere of negative radius. Theta runs from 0 to 2 pi, and the third angle phi measures from the positive z-axis going to the negative z-axis, so that one only goes from 0 to pi. Right? And again, if you visualise it, you should be able to work out that every single point in 3-dimensional space can be represented uniquely by a set of spherical coordinates. Yes? Yeah, this one book's doing it the other way around. Right? Different order to what we're doing. What I want you to do is look at the diagram, right? Which has got the coordinate plane. So what you can imagine this one is, so constant rho is basically, so that's its distance from the origin. So that just maps out a sphere, right? So you can imagine that the equation of sphere x squared plus y squared plus z squared equals rho squared, right? Which is a sphere centered at the origin. Now, then the other coordinate planes for angle theta, this is the same as the cylindrical coordinates, right? So theta measures from the positive x-axis going anti-clockwise, like this, right? So planes of constant theta are just half planes like this. But then the phi one, that's measured from the positive z-axis, so a constant phi, imagine you drop it a bit, so say that's phi, or from your, so you can see it, say that's phi is 45 degrees or pi on 4, right? And then if you were to draw that out as for constant phi, they look like cones, right? Like this, right? So you get these two open-ended cones, right? Right, so this one is, right, so cylindrical coordinates, just a logic extended polar. Spherical is one where we've got spheres. So, for example, the coordinates on the Earth are done in, everything we do on planets or the surface of the Earth or something is done in spherical coordinates, right, because it makes much more sense to do it that way. Right, we use it in the order as rho, theta, phi. Right, so there's two angles in this one. So rho is the radius of the sphere. Theta is the standard polar angle measured from the positive x-axis going anti-clockwise, and phi, the third angle, measures from the positive z-axis dropped down by a certain amount. Right? Right, so that's what it looks like, and the coordinate surfaces here are spheres, half planes, and cones. Right? So this is the relationship between them. You can do this with standard trigonometry and Pythagoras, just like what we do with polar coordinates. It's discussed a bit more in the unit reader if you wish, but essentially what you do is, imagine if we go back to this diagram, what have we got here? Right, let's say, that's the point, if that point P is x, y, z, to figure that out in terms of rho, theta and phi, well, I can figure out that length by Pythagoras. I know that length, so that there is a right angled triangle. It's just sort of coming out of the page a bit, right? So you can figure out the length of this one, right? And that's angle theta. You can figure out that length. From that you can figure out that length and that length. So you can figure out x, y and z in terms of these two angles, and this is what you'll end up with. X is rho cos theta sine phi, y is rho sine theta sine phi, and z is rho cos phi. And going back the other way, obviously we've set this up so they're cylindrical spheres, so rho is the same as the square root of x squared plus y squared plus z squared. And you can see that if this squared, that'd give you rho cos squared theta sine squared phi plus rho sine squared theta sine squared phi. Take out the common factor of sine squared phi. You'll get those, and the cos squared plus sine squared equals 1. So these two squared give you rho squared sine squared plus that, rho squared cos squared, rho squared square root rho. Right? So as you would expect, that's basically the equation of a sphere, x squared plus y squared plus z squared is rho squared. Right? Right, and here I've got some coordinates in standard Cartesian that I've mapped to either cylindrical coordinates and spherical coordinates, so you can get some practice with them. Right, but the main thing we're going to be using this for is figuring out integrals, right? Triple integrals that we can't or don't want to do in Cartesian coordinates. And as I said, there are actually lots and lots of coordinate systems, 3D coordinate systems. You use one matching the problem you're going on. So, I mean, this book's got a lot of really weird ones. All right, so here's one, for example, if it turns out the region you're integrating over is best described by ellipsoids, footballs. All right, so these are called prolate spheroidal coordinates, and there's your, that's your transformations for x, y and z. Awful. All right, so sinth and sinth they're hyperbolic functions. They're basically similar to exponential functions. But there's some really weird ones in here. So that's one if the footballs are orientated the other way. But there's some really wacky ones in here. I mean, have a look at this one. Right, so it depends on the problem. There's lots and lots, and sometimes you might be working on a problem where you have to come up with your own coordinate system. I had to do that once. That was very nasty. What we do nowadays, though, is you try and pick one somebody's already worked on, open this book, and it gives you all the results you need. Right, so we can cheat, basically. Right, but this one's tangent sphere coordinates. So the coordinate surfaces of this one are basically, they're basically dumbbells with a rubber band around it. Or a tube around it, or something like that. And there's all sorts of, it depends on the problem. Some of them are very strange, right? So cardioid ones, because if you squint, I suppose there's a shape in there that looks a bit like a love heart, right? And it's called the cardioid. So if you look down, what am I doing? If you look down here, right, it sort of bumps, right? It sort of looks like that, right? So there's all sorts of different coordinates. It depends on the problem you're doing, right? We're just going to do these two, though, because these two are by far the most common. Now, what we're going to do with these is we're going to have to be able to do triple integrals in these coordinate systems, right? So unlike when we do a change of coordinates in double integrals, where I might give you you might have to come up with a coordinate system or use polar, these ones it'll either be polar, cylindrical or spherical. I will never get you to do it from first principles. I think there is a question in the practical class either this week or next week that kind of illustrates the idea. I think it's the very last question. I'm never going to ask one like that. Right, but let's say we've got to figure out some triple integral, and the 3D region we're integrating over is best described in cylindrical coordinates. So we see that our change of coordinate, x is r cos theta, y is r sin theta, and z becomes xi, which when I'm doing it by hand, I just keep calling z because I hate writing that Greek letter, it's annoying. Right? We need the Jacobian, right? So remember the first row, partial dx dr, partial dx d theta, partial dx d xi. Right? So the first row is cos theta minus r sin theta is 0. Second one, partial dy dr, partial dy d theta, partial dy dxi. And then the third row, partial dz div r, partial dz d theta, partial dz dxi. So you basically get that matrix. We'll figure out its determinant, you'll find it's r. Right? So remember how we find the determinant, copy the first two rows. I give you this formula on the phone. You never have to do it again. Right? Basically, very similar. You place x with r cos theta, y with r sin theta, z with xi, although when I do it by hand, I don't bother doing that. Your correction, dr d theta dxi. Now, or dz. Now, as I said, with polar coordinates, unlike other double and triple integrals where we might have to change the order, this one, technically, it doesn't matter what order you do it in. You know, you could do r then theta then xi, or r then xi then theta, but don't mess with the order. Do it in this order, right? It'll just work out, right? Because what often happens is the angles will be constants, right? So your last two integration steps should be relatively straightforward, unless it's a nasty problem. In spherical coordinates, that's our change of variable. You figure out the Jacobian in this one, so again the first row, partial dx d rho, partial dx d theta, partial dx d phi, so on and so on. Right? You figure out the determinant of that awful mess, clean it up with the fundamental trig properly, eventually you'll end up with minus rho squared sine phi. Right? And you're not going to have to do this every time. I'm going to give this correction to you in the formula sheet. Notice it's negative though. Now phi, you remember, is the angle from the positive z-axis going down to the negative z-axis. So because phi runs from 0 to pi, and we know that sine's positive in quadrants 1 and 2, so sine phi is positive, rho squared is obviously positive, so that negative sign, we drop the negative sign when we take the absolute value. All right? So when we do the absolute value in our Jacobian formula, we just drop the negative sign, and then you replace x, y, and z with their equivalent expressions, right? And then times the density correction, d rho, d theta, d phi. And just like the other, don't mess with the order of this one. Right? So this looks horrendous, right? But it's actually not that bad, right? When the problems, it will be obvious, or I will tell you use cylindrical coordinates to solve this, or use spherical coordinates to solve this. Right? Now, I do want to go through one quick example before I discuss some of the others. I don't want to do that one just yet. We'll talk about that one. Is that the one I want to do? Yeah, that's the one I want to do. Let's have a look at this one. We're going to talk a bit more about these. Let's say I asked you to find the volume of this. Right, so remember, we can do a volume as a triple integral if we imagine we're integrating the function 1. Right? Right, so basically it's an ice cream cone. Right? Now, if I wanted to do that in Cartesian coordinates, how would I do it? Right? This would be awful. Right? Now, what would Z go from? Well, Z goes from the bottom, the cone bit, so I'd have to figure out what does a cone look like, how do I describe a cone in Cartesian coordinates, not too bad, to a spherical cap. Right? So Z goes from something awful to something really awful, right? Because it'll involve a square root. Right? And then I'd have I'd have X going from, well, if I'm in the cone bit, X goes from one side of the cone to the other, but if I'm in the spherical cap bit, X goes from one side of the cap to the other, and then sweep in Y. This would be absolutely terrible to do in Cartesian coordinates. Right? So, well, I see I've got a sphere and a cone. We saw that spherical coordinates are perfectly suited to the cases where you have spheres and cones, right? Because that's what it's designed for. Right, so if I wanted to describe this thing in spherical coordinates, how would I do it? Well, evaluate the volume of an ice cream cone described in spherical coordinates by these things. So basically, the top cap is a sphere of radius r. Right, so that's the upper bit. So you can imagine rho in this case, the radius of the sphere just runs from 0 to r. I want the whole sphere, so theta is the polar angle that goes like this. Right, so I want the whole cone, so theta goes from 0 to 2 pi. The way I've set this up, this is a cone that's got a 45-degree angle. So if I imagine theta drops, phi, sorry, from the positive z-axis drops down, right, that's the cone bit. Right? So if I was to describe this in Cartesian coordinates, all of my limits, my bounds on x, y and z would be awfully complicated. Here, in spherical coordinates, all constants. Nice. Right? Constant limits means life is good. Right? So I can say that the volume of this is basically a triple integral of 1, because I'm asking for a volume, right? 1 times the density, the correction, the Jacobian correction bit in spherical coordinates, which is rho squared sine phi. That's on the formula sheet. You never have to memorise it. Right? And again, don't mess with the order. Do it in the order I've given you. d rho, d theta, d phi. Right? So rho goes from 0 to r, theta 0 to 2 pi, and phi in this case goes from 0 to pi on 4. Integrate that first with respect to rho. Nice constant limits. The answer comes out nicely. Okay? Now, before we do a couple more examples, here's what I'd like you to do. First off, convince yourself that any single point in 3D space represented x, y and z can be represented in equivalent either cylindrical or spherical coordinates, and have a go at some of these, right? Taking a coordinate in x, y, z and finding its equivalent description in cylindrical or spherical. And remember, we never muck with the order. So cylindrical is always r, theta, z, and this is always r, theta, which is the polar angle 0 to 2 pi, phi, which is the angle from the positive z-axis dropping down, right? So have a go at converting a couple of those, and then we'll talk a bit more about some of the other examples in the next lecture tomorrow. Okay? All right. We'll leave it there for today. All right, don't forget to have a look at the sample test, and that you can ask your tutors if you want any, the practical people if you want help, or come and see me in my consultation time. All right, thanks everyone. I'll see you tomorrow.